is, basically, in my progression. So I might start running a test, and it turns out that after 2 years, 3 have failed. So there's 3 new failures in 2 years. Okay. This formula that's growing here is the formula for being able to calculate what that lambda is going on here. So I've had 3 failures. Okay, remember 3, it's the number of failures over the time you've been testing. That's the formula we had several pages ago. So this page, at this point in 2 years, I've had 3 failures, correct? Those 3 failures were tested for 2 years. The other 47 have also been tested for 2 years. So I could have done 2 times 50, but you'll see in a minute why I don't do that. Notice my color choices. Red is my first set of failures. In 2 years, 3 failed, and the other 2 were also tested for 47 years. So whatever this number comes out to be is my estimated lambda. As I continue my experimentation, it turns out I keep tracking my data, and at the end of 6 years, 2 more have failed, for a total of 5. My data, I'm basically paying attention to this last line. So at the end of 6 years, I've only got 45 left that haven't failed. 5 have failed. 2 since the last time I recorded the data. Okay. So this number 5 is always total failures. How many have failed? Straight on this calculation. This is the part that gets complicated. If you follow this technique I'm using to build the equation, you'll always get it right. 2 had failed at 3 years. I'm sorry, 3 had failed at 2 years. 2 more had failed at 6. And the remaining 45 have been tested for 6. The reason I don't combine these terms is if there had been no failures in 6 years, I'd still have the green term, I wouldn't have the red. But that becomes the formula based on that data for how quickly things fail. Do another line. The third line. At the end of 10 years, I've got 38 left that haven't failed. So 12 failures total, 7 more since that 6-year point. So I've got 3 failure terms. I know I'm going to have 3 red things down here and a green thing. So 3 failed at 2 years, that doesn't change. 2 more failed at 6 years, and 7 failed at 10 years, leaving 38 at 10. This is how it builds up. Okay. I'm doing the math, it's going to give you this column right here. This equation would give me this value. You'll have calculators in the test, so I know you'll get the right decimal. But you'll only get the right decimal if you write down the correct formula for yourself. Okay, let's continue the example. At the end of 12 years, hopefully it starts to look pretty routine to you as we progress here. At the end of 12 years, 2 more have failed, so I have another term, 12 times 2. Now I've got 36 left. So the red stuff here to the left, I'm keeping from prior iterations. And this number is always the total number of failures. Total number of failures over the total test time. So the test time is not 50 times 12 weeks. That's the big mistake people make. Well, you've been testing 50 things for 12 weeks. On its surface, maybe there's a certain logic to that, but it's just not true. Because I've got 3 that I only tested for 2 weeks, and I haven't tested them since. So the total test time is the complicated part of the formula. The biggest, most common mistake I see in industry is to just treat 50 times 12 as the denominator, which gives you the wrong answer. It causes you to overestimate the life of your product. As a quality engineer, don't do that. I see managers do that all the time. Even in Six Sigma training, where I've tried to emphasize not to. Their answer would be 14 over 50 times 12. They say that's my estimated lambda. And it's wrong. Okay? Continuing again. Okay? 14 weeks, I add another term. 15 weeks, add a term. Oops. So let's say there I stop my experiment. Sometimes experiments considered for a long time. This one took 15 years. So who knows what I was following. I was watching people drive by cars. I was keeping track of people that signed up for a clinical trial 15 years ago. I don't know what this data is. Okay? But if it's a clinical trial, then of the 50 people I started with, 24 have died over the years. Could be anything. I don't know what the defects are here, but the math is always the same. So you end up with this stacked set of formulas that look what changed. The numerator, each time I do the calculation, is simply the number of defects that have occurred up to that point. Okay. The denominator is always the test time of those failures. Okay. And that's one of the things you can test here, is take 3 plus 2 plus 7 plus 2 plus 4, it better equal 18. If the red are how long I tested the failures, so you can test yourself by making sure 3 plus 2 plus 7 plus 2 plus 4 adds up to that number. If they don't, you've dropped a term somewhere. So in this case, I've laid it out left justifies. You can see how once the red term is there, it stays. We keep adding more red terms each time we've got a new iteration. So the bottom one is our final estimated lambda. If you test until 100% have failed, your final green term will be 0 times something. You can drop it, obviously. You'd have nothing left. But most tests don't exhaustively go after everything. So what I've got here is my estimated lambda rate going on. I've got my early failure. Okay, the numbers are going down from 2 to 6 years. So I know that by 6 years I've probably stabilized, but in fact it comes back up again to 0.03. But eventually it goes to 0.037 and 0.053. So this data is not real accurate. If you want a really accurate experiment, collect the data every year or every 6 months. Notice I've got gaps here in the schedule. That might be because of the difficulty I would have collecting data. So you can only go with the data you're given. But given this data, I see a low point at here on my lambda. Okay. And then it starts to level off. So I know here I'm in my useful life, but it does start to climb in the 14th and 15th year. By the end of the experiment, I've got a lambda of 0.053, which is higher than any other point in my research. So I suspect I'm starting to approach the other end of the bathtub. Okay. That's what you're trying to deduce here. So it starts out high and falls a little, and then levels off, but it does start to climb. This data is not an obvious bathtub. This is a case where if after 15 years this is all I've got, someone's going to yell at me. Maybe you should have collected your data a little more accurately and reliably, maybe every year, so I'd have better data. But even with bad data, which I would say this is bad data. I didn't collect enough detailed data here to really draw conclusions. But I can see that my average life for this product is probably 25 to 30 years. And by the 15-year mark, my lifespan has fallen to under 20. So my hunch is I'm going to be offering a 10 to 12-year warranty on whatever this thing is talking about. If I wanted to be able to be a lot more precise than that, I should have collected better data. But I'm not going to give you a sheet on the test with 100 rows to it. That would be silly and a waste of your time. Okay? But as soon as you can see your data, one of the reasons this experiment might have stopped at 15 years is precisely because this number started to fall. So we know we're past an optimum point. Let's not spend 5 more years doing the research. But we know pretty much now we're looking at a decision point somewhere in the 12-year range. Offer a 12-year warranty because the life is going to fall off after here. So I'd be able to correctly hypothesize that if I continue the experiment, this number would keep going down. And if that's the case, I didn't need to do the experiment. Mean time to failure. That's the number you need to be able to calculate. Okay. What's it look like? Mean time to failure is the amount of time that it's passed for the failure. So at the end, I've got 24 failures in 15 years. Right? That's a 0.6 failure per year. So this is more averaging the failure rates across the lifespan. It's not telling you much about mean life. So that's basically the way the calculations work. Just opening up another one. See it. So mean time to failure, right there. It's the number. So this one's days, not years. So it's the amount of time you've been testing divided by the number of failures you've had. Very simple calculation. Okay. So if in 7 days one failed, you have a mean time to failure of 7 days. Down here, for that 3.7 is our 22 days of testing divided by the 6 failures. Okay. So mean time to failure is a pretty easy calculation. If you've got the amount of time and total failures. So this has nothing to do with how many have failed in the last couple of days. It's total, over the whole range of your test, how many have failed. Where this is the cumulative number over the whole thing. And then life days, this is simply the reciprocal of this. So if you can calculate that number, which is always the hard part for everybody, take its reciprocal and you've got that. So it's purely 1 over the lambda. Okay? Again, I'll do this fairly quickly. We'll go back through it again on Thursday when we're talking about